Alright guys, so this is our last Flip the Classroom lesson of the first semester. We're going to break this lesson up into 3 videos, and this is the first of these 3 videos. And this lesson is going to be on the graphs of the other 4 trig functions. So right here, before break, we talked about how we can take the ratio of sine and graph it as a function, right? And what we said was, basically, we can take sine and say that sine of x is going to evaluate inputs of rotations that we can define as theta. So we take some rotation theta, right? Sine takes that theta as an input and gives as its output the vertical change that angle creates, which we can see as basically the ordered pair on the perimeter of the circle, the y value of the ordered pair on the perimeter of the unit circle, where that terminal side ends. And so right here we're saying basically a function develop which takes its inputs as rotations on the unit circle and its outputs as vertical change, or the y value on the perimeter of the unit circle. Similarly, we can say that the ratio of cosine can be defined as a function when we take the inputs as the rotations and the outputs as the horizontal change that those rotations create, or the x value on the perimeter of the unit circle. So right here what we've got is basically 2 functions that are taking rotations as inputs, and the x values and the y values on the perimeter of the unit circle are their outputs, which we would define as their function values. Now, what we're going to be able to say for the other 4 trig functions is that we can define them in a very similar way, right? So right here, for tan x, we can say that tan x is going to take as its input a rotation, or some theta, and its output, or its function value, is going to be defined by the ratio of the y value to the x value in the perimeter of the unit circle where that rotation ends. So right here, we've got a y value defined on the unit circle as the y value divided by the x value on that terminal side. So right here, similarly, we can say that cosecant of x can be a function defined by taking inputs as rotations and outputs as the ratio of 1 over the vertical change that angle creates, or basically 1 over the y value on the perimeter of the unit circle. So the function values, the y values of cosecant, are defined by 1 over the y value on the perimeter of the unit circle for the terminal side of that angle. Now right here, secant of x, similarly we can say that secant is going to take inputs of the rotation and define its outputs with 1 over the x value on the perimeter of the unit circle. So the y values for secant are going to be 1 over the x value on the perimeter of the unit circle, and cotan is going to take inputs of the rotation again and define its y values, or its function values, with the ratio of x to y on the perimeter of the unit circle, where that angle has its terminal side. So just to be sort of specific here, we're saying that basically wherever that terminal side meets the unit circle, right, that ordered pair are defining the x and y values that we are using to define these ratios. So basically what we've got is 4 functions coming from these other 4 ratios. And we're going to see one big difference with these other 4, with the graphs of the other 4 trig functions from the graphs of sine and cosine. And that is that the ratios that are defining these trig functions all have variables in the denominator that can equal 0. The x and the y on the perimeter of the unit circle equals 0 when we rotate onto the x or the y axis. And what this is going to mean is vertical asymptotes. In the graphs of these other 4 trig functions, for thetas, or rotations, that give x values of 0 or y values of 0. Right? So we're going to start seeing vertical asymptotes for thetas that have x values of 0 or y values of 0. So right here, what we're going to do first is take a look at the graph of cosecant, and what we're going to do at the very beginning is sort of say, where are we getting those vertical asymptotes? Well, we know that cosecant is defined by 1 over the y value on the perimeter of the unit circle, And the y value on the perimeter of the unit circle is 0 when we rotate onto the x-axis, right? And basically what we can say here is that a rotation onto the x-axis is going to be a rotation that is an integer increment of pi. So right here we've got 0 pi. If we rotate over to the negative x-axis, we've got pi. A full rotation would be 2 pi. A rotation and a half would be 3 pi, and onward like that. So basically what we're going to see for the graph of cosecant x equals y is vertical asymptotes at integer increments of pi, because those are the rotations that land us onto the x-axis, giving us a y value of 0. Now, what we're going to do from here is basically talk about what one period or one full rotation of the cosecant ratio is going to look like as the function cosecant of x. So next what we'll do is look at what happens when we rotate onto the y-axis, right? So a rotation of pi over 2 is going to give us a y value of 1, right? And that's going to give us a ratio of 1 over the y value of 1, which means that we're going to have a function value of 1 at the rotation of pi over 2. If we rotate all the way over to 3/2 pi, now we've got a y value of -1, right? Which is going to give us a 1 over -1 for that ratio of cosecant, which gives us a function value of -1 at the rotation of 3/2 pi, right? Now, what we can say about these ordered pairs, right, is that the y values that define the ratios there are basically the greatest y value and the least y value that we're going to be able to plug into that ratio, right? So all other y values are going to be decimals, or sort of numbers less than 1 and greater than 0, or greater than -1 and less than 0, right? And if we start dividing 1 by numbers in between 1 and 0, what we know is that we're going to get larger numbers for that ratio, right? So really right here what we're seeing is that this first ordered pair that we get for a rotation of pi over 2 is actually going to be a min, because all other rotations are going to give us y values that are smaller than 1, giving us basically larger ratios. And this rotation, this ordered pair that we get at the rotation of 3/2 pi is going to be a max, because we're going to be dividing by negative numbers that are greater than -1, or basically between -1 and 0, which basically means larger negative numbers for the outputs, right? And so what we're going to do now is take a look at the graph of this. And right here, I'm going to shift this a little bit. We're going to sort of create this on our own, so I'm going to start over here for us. Right here, what we can see as we rotate, right, we start out with a y value of 0, basically at our vertical asymptote. And as we rotate through the first quadrant, right, what we're basically seeing is really small y values at first, which are giving us very large outputs. And then those y values get larger and larger in the denominator, all the way up to 1, right, giving us that min at pi over 2 of 1, right, for that first quarter. Now right here, what we can see is as we rotate through the second quadrant, we're getting y values that go from 1 and start decreasing to 0. So we're basically going back up into that vertical asymptote for the second quarter of cosecant. Now right here, when we rotate into the third quadrant, we start out with y values that are negative and really, really small, which are going to give us really large numbers, large negative numbers though, for the ratio of cosecant. And as we rotate through that third quadrant, we get those y values going all the way down to -1, which is going to give us a max right there at 3/2 pi of -1. And as we rotate past 3/2 pi, the y values on the perimeter of the unit circle are going to get closer and closer to 0 from the negative side, basically taking our graph back down into the vertical asymptote at 2 pi. And this is a graph of cosecant. Now we're going to analyze this graph real quickly, and then I'm going to let you guys try to graph secant. Right? So we'll sort of get our graph right here. This is one period. one thing that we can say is as we continue to rotate around the unit circle, right, basically we're going to be cycling through those same y values over and over again. So just like sine and cosine, we're going to be able to say that really this first full cycle, or this first period on the x-axis is just going to be repeated over and over again. So I can basically go back a length of 2 pi and take my max, or my min rather, right there, and my max right there, and go ahead and graph another period, and I know that it's going to look the exact same because I'm really rotating through those same y values on the perimeter of the unit circle. So right here, looking at the domain of cosecant, the function cosecant, we can say that really we're going to be able to evaluate all rotations as x values on the x-axis, right? Except for those rotations that are giving us 0 y values in the denominator, so those integer increments of pi. So right here we can say our domain is going to be all real numbers, where those real numbers are rotations in radians, all real numbers, and then except the vertical asymptotes, which are x equals k pi, where k is an element of the integer. So k is an integer, right? The range right here is going to basically include all y values except for those y values between our local maxes and mins. So we can say then that the range would be from negative infinity to negative 1, where we have that local max, union with, and then 1 to positive infinity, right? Are we symmetric? Well, right here we can see that we are getting points reflected across the origin, so that means that we are an odd function, symmetric with respect to the origin rather. We are unbounded, so we would say bounded, and I'm just going to say no. Local extrema. So right here what we can basically see is that we're getting maxes and mins, and we're just going to say what the y values of those maxes and mins are, and we'll talk about how we can define where they are on the x-axis in class on Wednesday. So right here we'll say that this is a max of, we're going to have maxes of y equals negative 1 and mins of y equals positive 1. And we can see that the asymptotes are basically those holes in the domain, so those are going to be x equals k pi, where again k is an integer. So right here, here's an analysis of the graph of cosecant. What I want you guys to do is to give the graph of secant a shot, and we'll come back and look at it and do it on the graphing program as well. So pause the video and give this guy a shot. What I would say is, as far as the strategy goes, you want to basically define where you're going to have your vertical asymptotes, and then maybe look at ordered pairs generated by the other axis, or the other axis that isn't giving you vertical asymptotes. A little hint there, and then try to get the graph from there. Okay, so give this a shot. All right, so what we're going to do now is basically start to construct this graph of secant. We've got vertical asymptotes that are going to happen at rotations that give us 0 in the denominator. Since secant is defined as 1 over x, that means rotations that give us 0 x value on the perimeter of the unit circle, which are really rotations that land us on the half increments of pi. So we can go through and draw a vertical asymptote at half increments of pi, right? Or maybe not exactly half increments, maybe we would say odd half increments of pi, like 1/2 pi, or 3/2 pi, or if we rotated continuously, we might say 5/2 pi, 7/2 pi. Those are rotations that land us on the y-axis and give us an x value of 0. If we look at rotations that land us on the x-axis, right, we can see that we're getting either 1 or negative 1. So right here, at a rotation of 0, we're seeing the function value of 1 from our 1 divided by the x value of 1. And at pi, we're seeing a function value of negative 1 for the secant ratio of 1 divided by negative 1, which would give us, of course, a function value of negative 1. And then right here, 2 pi, we land back on the positive x-axis, so an x value of 1. And right there, that's going to give us the ordered pair of 2 pi positive 1. Now, just like we took note before, we can do the same thing here. Really what we're seeing is that 1 is the greatest x value we're going to divide by, and negative 1 is the least x value we're going to divide by. So really what we're going to get are numbers between 0 and 1 and 0 and negative 1 that we're dividing to create this secant ratio. We're dividing 1 by those numbers to create the secant ratio, which means that our outputs are going to see a min of positive 1, right, and a max of negative 1, just like we saw from the graph of cosecant. So right here, we're going to go to our graph. We start out with that x value of 1, and as we rotate through the first quadrant, we're going to see those x values go from 1 and decrease to 0. So we're going to see this ratio basically get really, really large. So rotating through the first quadrant, we start out at 1, and as those x values created by the rotation get smaller and smaller, we see the ratio values go all the way up to positive infinity into that vertical asymptote at pi over 2. Rotating into the second quadrant, now we've got very, very small negative x values that we're starting with. So we're seeing our ratio values come from negative infinity and go all the way up to negative 1 when we reach the x value of negative 1 for a rotation of pi. And then as we rotate past pi, those x values are getting smaller again, going back to 0 from negative numbers, And so right here what we're basically seeing is the secant function values go down to negative infinity into that second vertical asymptote of 3/2 pi. Now, as we rotate into the fourth quadrant, those x values are now positive again, and we start out with small x values, and basically that means really large ratio values for secant, and those ratio values get smaller and smaller as the denominator with our x values gets larger and larger, going all the way down to 1. So basically, it's that same sort of looping effect we saw for cosecant, except for we're starting at that min right now and going up to positive infinity. And then right here, we're seeing that second loop go up to the max right there at pi, and that last piece on the other side of the vertical asymptote at 3/2 go from positive infinity to 2 pi. And basically right here we can say that this pattern is just going to repeat, just like cosecant. As we rotate around and around, we're really cycling through the same x values that are giving us those rotations, so we can go backwards and define another period of secant in that same way. Now right here we can do a little bit of quick analysis. We can say that our domain is basically going to be all real numbers except for the real numbers that are giving us 0 in the denominator. So this is all real numbers except for the rotations that are giving us 0 in the denominator. And if we look at this, we can say that those are going to be increments of half pi. So we can start at pi over 2, and then if we add k pi, where k is an integer, we're always going to end up on an odd half, which is going to basically give us that vertical asymptote. The range again right here, we can say is going to go from negative infinity to negative 1, that local min, just like cosecant, and from 1 to positive infinity, right, where negative 1 and 1 are both included because they are the local max and local min. Symmetry, we are symmetric with respect to the y-axis, which makes us even. And then right here, boundedness, we can say no, because obviously we're going to negative infinity and positive infinity with our vertical asymptotes. Local extrema, we're going to define those by the y values for right now. So we'll say this is a max of y equals negative 1 and a min of y equals 1. And right here, as far as the asymptotes go, those are the holes in the domain. So we're going to say that we have vertical asymptotes at pi over 2 plus k pi. And that is the analysis of secant. This is the end of this video. We are going to go ahead and graph the tan and cotan functions in the next video.